Couple problems on coloring proofs. So first problem is the following. We are given a 5x5 board and a beetle on each cell of the board. At some point, this is a random process. At some point, all beetles move from one cell to another to adjacent cell, and then will this necessarily leave an empty cell. So there are 25 cells, 25 beetles. All of them will move to another cell. None of the beetles stay at the same place. And will that necessarily leave an empty cell? The answer is here, obviously no. So we want to prove why it's not possible, because if it's possible, we would just show an example how this would happen, and then that would be the answer, right? So 5x5. The trick here is 5x5 board. The amount of beetles is 25. So if it was a 6x6 board, the amount of beetles would be 36. Then you would pair the beetles, and then they would switch their places. And those 36 beetles would cover the board again after that random process. Maybe even if you do so, it will not necessarily leave an empty cell. There is a scenario where it will still keep covering the board, but with 5x5 board it's not the case. So we want to prove why it's not possible. So let's take a look at one beetle. So it can move to one of these 4 yellow cells. And the idea is that if you look at this small part of the board, 3x3, you can see that already is alternated coloring. Black, yellow, black, yellow. So if I just do black and white coloring of the board, so I just make a clustering of the cells of the board. So there will be some of them are black, some of them white, and then white cells will have some property, black cells will have some property, and then I'm going to compare them. That's the idea. Otherwise, initially we have just cells and then beetles, so undistinguishable cells or beetles. We need some place to hold hands, then start working on that. So I'm going to divide into 2 groups. So if you do that, there is one simple pattern that you can see. A beetle that's on a white cell will always move to a black cell, because the neighbors of the white cell is black and neighbors of black cell is white. So basically we will have beetles that are on white cell and black cell. So you can just call them like white beetles, black beetles. So if you bring back all the beetles and paint it like a chessboard, you can see that there are 12 white beetles and 13 black beetles. So after this random process happens, after this described random process in the problem happens, all 12 white beetles will move to black cells, right? So take this. These 12 white beetles will move to black cells. So, but the problem is the amount of black cells is 13. So only 12 white beetles will not be able to cover all of them. One of them is going to be empty anyways. What will happen to black cells, black beetles? They will go to white cells, but the number of white cells is 12. It means that some of the beetles that were on black cells originally will move to white cell together. So they have to 13 beetles will have to fit into 12 cells. So which basically means there will be at least one black cell empty. No matter how this random process happens, there will be one empty cell. So that kind of proves the idea. It will always leave an empty cell because the number of beetles with white property and then black property, they are not equal to each other. So the idea in these problems is when you are given some kind of data to work with, you have to identify some features of the data which is not initially given. So when you identify the features of the data for visualization purposes or for organization purposes, you could say whatever you like, you can just paint them, assign them colors or assign them numbers so you can distinguish between them. So here we just assign colors to the cells of the board. So after painting it, we have like white cells and black cells. So another problem, is it possible to cover 10 by 10 Tetromino by 25 straight Tetrominoes? So 10 by 10 board is here, straight Tetromino is like 1 by 4 domino, like it's like a figure. So the problem here, since 10 is not divisible by 4, if you try to put just if you try to do the tiling straightforward, put one Tetromino and then another one, you cannot put the third one here, right? Because the third one will overflow the board. So which means you have to make it vertical. So you can put there 2 vertical Tetrominoes and then go back to the right, to the left, and then like a snake. But if you pause the video and try to fit 10 by 10 board by 25 Tetrominoes, technically, so since there are 25 Tetrominoes, like 4 cells each, like 100 cells, that should cover 100 cells, and then 10 by 10 is 100. It should be okay, but if you try to do that, it's not possible. So now we want to prove why this is not possible, why it's not possible to cover by 25 straight Tetrominoes. So in order to do that, I'm going to paint the board in 4 different colors. This is going to be some kind of assigning colors and then different perspective to the board. So the main diagonal red, and then the next diagonals are green, and then blue, and then white. So what's interesting about this painting is that no matter how you place your Tetromino, it will cover one of each color. So you can just play around and then see, no matter how you move, you can even move it vertically, place it vertically, and then you'll still get one of each color. So which means if I'm able to cover with 25 Tetrominoes the 10 by 10 board, it means I will cover one of each color. So that would make like 25 colors of red, 25 for green, 25 white, 25 blue. Or imagine if there are more than 25 colors of something. Like if there is more than 25, then it means I need more than 25 Tetrominoes. So basically here, if I just count the red cells, so that's the contradiction we are going to show as a proof. If you count the red cells, the amount of red cells on the main diagonal is 10. Here you have 6. So 6, like 10, 22 plus 4, 26. So basically we have 26 red Tetrominoes. How many Tetrominoes do you need to cover 26 red cells? Since one Tetromino can cover only one red cell, it means you need 26. So in order to cover 10 by 10 board, you will need at least 26 straight Tetrominoes. That means like there will be some overflow, but it's not possible to do it with 25 Tetrominoes. And the final problem is it possible to cover 10 by 10 board by 25 T-Tetrominoes? So here is the board again. We have T-Tetrominoes in this shape, like Tetromino. It has 4 cells. So for this problem, you can just imagine different types of paintings of the board and then try to come up with some kind of contradiction. So the answer is obviously no, but how you prove it? So so at least like there are several different types of paintings, and then different types of paintings could work for this problem to prove, because this is an easy one, and I'm going to use the most straightforward chess painting. Imagine we have black and white 10 by 10 chessboard. If you place this Tetromino on a chessboard, what will be the coloring of the Tetromino? So it will be 3 whites and 1 black, or 3 black, 1 white. So now you can do some kind of small, like simple math. So since we have 10 by 10 board and black and white, each of the colors, so we have like 50 black cells, 50 white cells, but we can count it in a different way using these Tetrominoes. Imagine that we were able to cover it by 25 Tetrominoes. The number of white cells would be each of the first type. This type has 3 Tetrominoes, so that means, say, we have X amount of the first type and Y amount of second type. So if you want to count the white cells, that will be 3 times X, because the first type has 3 white cells, and then plus Y. And if you want to count the black cells, that would be 3Y plus X, because second type has 3 black cells. Now if you want to figure out what's X, what's Y, you can solve the following simple equation. And then how many of the first type and how many of the second type. So let's say, just do simple substitution. Y is 50 minus 3x, and then put into the second equation and open the parentheses, get like, so 8x has to be here, this one has to be 100 in order to get 50. So this is here, x has to be 100 over 8, and x is 12.5. We cannot have non-integer number of Tetrominoes, so x has to be, this x has to be integer number. We cannot have like 12.5 Tetrominoes. So that brings us to a contradiction. It's not possible. If we were able to do the covering, then we would need a non-integer number of Tetrominoes, like 12 of first type, 12 of second type, and then half of each. So that's not possible. So that's not, like, we are not going to split in halves. So that brings us to contradiction, which says that it's not possible to cover the board by 25. It's not possible to cover 10 by 10 board by 25 Tetrominoes.